With a small disclaimer that this is not a research talk, but I was asked to give it, so let's say it's not my fault. BD in the title, that stands for Battling Vilkovisky. And it is some method in quantum field theory, in, say, perturbative quantum field theory, and I'll be talking about basically the difference, very elementary differential geometry, which is behind that method, which explains what's happening there. And really, what it is about is it's about a link between symplectic form and symplectic forms and volume forms. Okay, there is a lot to be said about the volume forms in symplectic geometry, but for sure there is a canonical volume form, the Liouville volume form. But things become slightly different or sort of more interesting in supergeometry when the symplectic structure is odd. So this is what is going to happen. So I'll be talking about odd symplectic supermanifolds. And if you're not feeling very familiar with supermanifolds, just don't worry, it's going to be quite easy. So what are these? I will just write down what it means, and then I'll give you an example which should hopefully explain everything. So, okay. So what should it be? These are just, such a thing is a supermanifold with a symplectic form. So omega is a symplectic form, so we have the omega is 0 and omega is non-degenerate. And odd will now mean that omega is odd. Okay. Very well, so I'll give you this typical example which might explain everything. So we start with an ordinary manifold. So this is not a supermanifold, M0. And then for M, we just take the cotangent bundle of M0, but change the parity of those fibers. So what does it really mean is that now the algebra of functions on M, that's simply the algebra of polyvector fields on M0. Polyvector fields. M0, and I'll denote it by this kind of V. M0. And so, what kind of thing is that? Well, it is a graded commutative algebra, keeping the Z2 grading. So, at least at this moment, forget about the fact that it's Z graded. We only care about it being a supermanifold, so it's only the parity which matters here. And it has a Poisson bracket. It has an odd Poisson bracket, namely a Schouten bracket. And that's what corresponds to this natural odd symplectic form that you can imagine that somehow lives here. Poisson bracket. Is this called then? And to what extent is it a representative example? In fact, there is a sort of result like this, that every M is symplectomorphic to one of these guys. So it looks sort of disappointing that there are not too many examples. The symplectomorphism is not canonical, so at least there is something. Let's say there are not many objects, but there are many morphisms. So one shouldn't get overly attached to that fact. If I can tell you a proof. So proof is like super easy. If you start with an odd symplectic supermanifold, now you take the body, which is the true manifold sitting inside, and when you restrict the symplectic form there, it becomes 0 because the form is odd. So there are no odd things on a true manifold. So it's a Lagrangian subspace. And then you just simply use the Lagrangian neighborhood theorem. That is the end of the proof. I can weaken it in this way. So why one shouldn't get overly attached to such statements? Because, well, as in geometry, one should always consider families of things. Even if you consider them just locally, in supergeometry we should consider families parameterized also by odd parameters, by say over base with odd coordinates, and then this statement is no longer true. So if you imagine that epsilon is this kind of odd parameter, so then we can get a symplectic form of this type that I would take omega 0. This is the one. Sorry, maybe it's not a good notation. It's the one which appears here, and then one can add epsilon times any now closed true form on our M0. Omega 1. Probably I should write here something like P star or something. P star omega 1, for P is the projection from phi P star M0 to M0. So this is a kind of counterexample if we admit odd parameters, and so the true moduli space as can be sort of be seen from here is really H2 of M0 with real coefficients. So if I'm staying with real numbers and parity change. Okay. So this is, but in the end I'll be basically talking about polyvector fields. And now the statement is that there is no natural volume form here. And why is it? Well, if you take if you take a function, meaning a polyvector field, we cannot really integrate it, right? So if there was a volume form, we could just integrate it against the volume form, but there is no such thing.
Sorry, just an equation, and if I try to build something like a linear form, I just take those powers What's wrong, or what, I mean, what?
What's wrong? There is some one little thing is wrong, that volume forms are not really differential forms in secret geometry, but it's not such a huge deal. The trouble is that if you take omega squared, then you get 0. So once you start taking those powers, you fail very, very quickly.
Okay.
Yeah. So there is no natural volume form.
Or is it because, like, it will be whatever symmetric in some in the Topology?
Yeah, or whatever. Maybe, okay. Let me write it like in coordinates. Yeah, so if omega is something like dxi times dpi, yeah, and then as you said, that if you just imagine taking these twice, and it's always like that the parity of x is opposite to the parity of p. And somehow things conspire in such a way that omega squared is equal to 0. Okay, so there is no natural volume form, but still some volume forms are more equal than others. So it's not quite that, okay, there is no invariant volume form, but some of them are better than others. And this was this led to a lot of amusement, apparently, when people were trying to understand it. So the story originated, okay, besides Batarin and Wilkowiski, this geometric story comes from Albert Schwartz. But the story was really finished off by Johannes Hudaverdiano, who really understood what was behind it. So I'll write the theorem. I don't know, I somehow, since I'm no longer teaching with blackboards, I'm not able to write with chalk.
No, the impressive name looks very good.
It should look like this. Okay, so the theorem has several parts, one can say. And part of the story is that one shouldn't concentrate so much on volume forms, but rather on their square roots. So one should really concentrate this person, and since then everybody else is talking about half densities, but there are no, let's say, there are no absolute values there. So I'll be freely talking about densities and half densities, but there are no absolute values of what were determinants entering. So just take it like that. So there is part 0, let's say, of the theorem, who says that actually one can take square roots in a natural way. So part 0 says that there is a natural square root. So beta 1/2 m. Okay, so what I'm supposing that m is odd symplectic. Of the bundle so this kind of would be a line bundle of half densities and of the bundle of densities. Beta. M. Beta stands for Berezinian, so it's some kind of complicated thing. I'll comment on it a little bit later. For the moment, just imagine there is some line bundle whose sections are densities or things that might get integrated, and it admits a natural square root if we have odd symplectic structure. So there is some relatively easy statement. And maybe I'll be denoting, okay. Let's get point 1, which is maybe the most important part, that we said that there is a natural differential operator acting on those half densities, on these square roots. natural differential operator delta on those graph densities, which is given explicitly, so given in Darboux coordinates by simply as the sum. And now this thing. So, okay, for sure.
In the coordinates and under some trivialization, right? You're saying that you have some kind of trivialization of
Yeah. So, okay, so I should to explain a little bit more about this guy. So now I somehow want to identify those half densities with functions. Let's say if once you choose coordinates, then densities are automatically identified with functions. There is some kind of preferred, or for example, okay, just take the ordinary integral basically in coordinates. Now, yeah, for half densities, this might be up to a sign. So this is slightly less clear. So you are totally right that if I say that there is a natural square root, that there should be also somehow a natural choice here. But here we can just pretend that if it's up to a sign, it's still perfectly fine. Nothing would change if we multiply every half density with -1. The same operator would stay the same. Okay, so what is actually the content of this one? Of course, one can write down this differential operator. The content is that it's natural. That if you pick a different set of those Darboux coordinates, then we get the same thing. Okay, then this operator has some fun properties. So what are those properties? So for one thing, it's odd. It's kind of clear that every time one of these coordinates is even, one of them is odd. So it is odd. Its square is equal to 0. It's sort of similar to the fact that square of omega is equal to 0. So it's a differential in the end on the space of half densities. It's a second order differential operator. Probably I don't have to write it down, but it is formally self-adjoint. I mean, the way it's written, there are only second derivatives, so it is formally self-adjoint. But it makes sense because it acts on half densities. So if you multiply two, this kind of inner product would be on half densities. If you multiply two, then we can integrate them, modulo some orientation or something like that. And the final property is one I call Cartan magic formula, which says that for every function on our M, if you take the commutator, the graded commutator between this operator and f, or maybe I can write like f dot, I mean the multiplication operator by f, then what we get is the Lie derivative with respect to the Hamiltonian vector field. So what this basically then says that Hamiltonian vector field will act trivially on the corresponding cohomology, right? So there is an explicit homotopy saying that it's. And property 3, that is the last thing, don't worry. Property 3 is the thing which is actually used in that, for the moment, undisclosed Batarin-Birkovitsky formalism, which will be disclosed right after this theorem, hopefully. So property 3 says that there is some link between all of this stuff and Lagrangian submanifolds. And that's kind of maybe the most fun part of the story. So if L part of M is Lagrangian submanifold, or supermanifold, I should say, Lagrangian, let's say that L is locally given by, in Darboux coordinates by setting all p's to 0. So let's choose locally some Darboux coordinates. So L is given by all those pi equal to 0. Then there is some, it's a distributional half density which supports on L, which is somehow very nice. So there is then delta L, which is one of those half densities, 1/2 M. I'll write prime here, meaning that it's a distribution given in these coordinates simply as the delta function. So delta L is given by the product of this delta pi I. Yeah, where I really now need to say that there is an identification between functions and half densities. So this guy is first of all well defined, so it doesn't depend on the choice of those Darboux coordinates. So delta L is natural. So well defined and closed.
So you chose those odd coordinates to vanish, but you could have chosen some of the even ones or all the even ones?
Yeah, I'm not insisting on x's to be odd, even, and p's to be.
Okay.
They can be everywhere also. When I wrote that thing, it could have been like that. Okay, so that's the end of the story for the theorem. As you see, it's a. Let's say some people might be not totally satisfied with all those coordinates appearing and saying that it's independent of those choices. I'll tell you the right way how to do it in a moment, but that is perfectly sufficient. So let me tell you maybe what's happening in this example, which is anyway kind of every example.
So in this example, do we know what happens with the homology of delta, since it's a...
Yes.
Mm-hmm.
Yeah, we'll know everything. As I said, it is really elementary differential geometry. So there is nothing. Just besides the fact that there are supermanifolds, everything is really silly. So this example, when M is equal to pi t star of M0, and so functions are polyvector fields on M0. So what are then those natural half densities? Those natural half densities, they can be naturally identified with differential forms on M0. Now, this guy, these are sections of some line bundle, so it better be kind of rank 1, whatever locally free module of this guy. So how is it a module? It's module by contraction. VM0 module by contraction. What else is it? If I say that these are half densities, so there is a natural pairing of half densities, right? So we just multiply them and then integrate them in modulo some orientation issues. So what is that pairing? So this was just my notation for like multiplying two half densities and integrating them. Well, this is the only thing one can possibly imagine, that we take those differential forms, multiply them, and integrate them. So it's the integral of alpha wedge beta over M0. What is the delta? Again, there is nothing that it can be, nothing else it could be. Delta is the Ram differential. Anything else? Yeah, the last part of the story. How about that L thingy? I will not give you like everything, but at least if L is the conormal bundle of some submanifold in M0, so if what L is equal to, okay, it should be called pi n star of some L0 part of M0, just a submanifold. So then, yeah, I should explain somehow a bit what's happening with this delta L. Let me just do it that way, that if I pair it with another half density, say with a differential form, okay, so this guy should be some Derham current, and it's the Derham current which is assigned to L0. So let me write it that way, that this is the integral of alpha over L0. So did we learn some? Okay, one can now have a feeling that this is about nothing, but it's not true. Because for one thing that you might observe, so there is some sort of fake product here, but it's then integrated. So what's missing really here is the product of differential forms. So differential forms come with contraction by multivector fields, with their differential, with integration, with all whatnot, but they are not algebra, really. And why are they not? Because all of these things, they are invariant with respect to sympactomorphisms, but the product is not. So, and this actually plays an important role somewhere in something which is called the calculus operand, which well, I might talk about later, or maybe not if I don't have time. Okay, and I should now tell you something at least about this Batalin-Vilković formalism. So let me put it this way, that say a summary of the theorem. It says simply that those half densities that they say that guy is a complex with a pairing then naturally descends to the cohomology, and XF acts trivially on the cohomology. Okay. I should be here a little bit more careful because, you know, maybe one should consider half densities with compact support to be able to actually pair them. But this is then often too much, so it's better to rather have one half density with compact support and the other one arbitrary. So there are really like then two complexes. So one with compact support and one without compact support, which would correspond exactly to differential forms with compact support and without compact support. So no surprise here. And moreover, you see, when there were these distributional things, so if I admit those, I should admit them only on, say, on one side, or make sure that the wavefronts of those distributions they are transverse or things like that. So, but let me just keep it that way, and all those little technicalities you can probably resolve them easily. And so, how is it now used? So this BV normalism. So the thing is that, let's say, in quantum field theory, you want to compute some integral which doesn't make any sense. Normally, that's probably the definition. And so the integral would be, let's say, some partition sum or something. And you write it in that form that it's actually the pairing between delta L for some particular L that you choose, and some alpha, where this alpha is actually and this is, in that context, this is called the quantum master equation. So it's a very important equation, definitely. Quantum master equation. And you shouldn't forget that delta L is also closed automatically. But so what is this, guys? In the end, it's some sort. Basically, it's an integral of kind of alpha restricted to L. But in quantum field theory, the way you compute the integrals is that you can only compute the Gaussian integral or a Gaussian integral, and then some kind of perturbation of those things. So you need to have some local minimum somewhere or something like that with non-degenerate Hessian, and then you can do stuff. But very often, when people write it down for some gauge theory, somehow in a natural way, then this is not true. So this is some kind of formal integral which doesn't make sense even perturbatively, because things are too degenerate. We cannot make this machine run. So then the idea is to replace L by some deformation. So let's say this is impossible. To compute, meaning impossible to define, really. The reason being that now we are somehow, which I didn't mention, but now we're in infinite dimension and things are just horrible. But the idea is to deform L to L prime. Let's say by some Hamiltonian diffeomorphism of our underlying all-simplex manifold. And then, you know this, when we now take delta L prime and alpha, if you compute this thing, then because we just deformed L to L prime, then the cohomology class of L prime is equal to the cohomology class of L. So why is it? It's because of that. Right? As I said, Hamiltonian diffeomorphisms act trivially on cohomology. So what do we get? It's the same thing, right? So this is Z. again. And if one chooses this deformation in a nice way, then all of a sudden this, whatever the Hessian of that function that we actually need to integrate somewhere becomes non-degenerate and can be computed. And then this is basically then used as the definition of the Z. If this was mysterious, then it's fine. I really wanted to talk about that elementary differential geometry and not about this horror, but let's say this is the motivation and also the source of everything in this story.
Maybe just an equation, but how is it? So, those integrals which cannot be defined, right? That's because some transversality doesn't work or something. But then eventually, should we think that one day maybe this derived geometry will come there and will define the undefined integrals? Or I mean, is it?
Yeah, it's possible it even came there, or
okay.
just those ordinary mortals didn't notice.
Mm-hmm. Okay.
Yeah, why not?
So it sounds reasonable.
Yes, of course. Like basically, every nonsense is in the end true, but.
Mm-hmm. Okay.
Maybe let's say one little remark is that even though all of these stories are really like 20 years old or even older, with the story with half densities, people are still not totally happy with it. Maybe so they still want to just work with functions and things like that. So what's really happening there? That if you imagine that if some alpha 0 is a closed and invertible half density. So it's closed. I mean, okay, or not everywhere non-zero. But it's a section of, okay, it's a section of a line bundle. I mean that it's everywhere non-zero. So what can we do then? Then we can, of course, using this alpha 0, we can identify half densities with functions. C infinity of m. So this becomes isomorphic by multiplication with alpha 0 with. And so then we get a delta acting here. So then we get some kind of delta, let's call it delta alpha 0 acting on functions. And now the properties of this guy, so this makes delta alpha 0 makes the algebra of functions C infinity of m to what is called a Batalin-Vilkovitsky algebra. BV algebra. But what does it mean? It simply means that we have that this guy is a differential, so it's an odd and so delta alpha 0 squares to 0. It's odd. It kills 1. We cannot say anymore that it's self-adjoint, so it has only this very weak property that of 1 is equal to 0. And the symbol of this differential operator is the Poisson structure. Delta of f times g minus delta f times g, and now minus plus f times delta. But this is the Poisson bracket between.
Oh, you know, but now I'm really confused, right? So we traded, so you explained to us that the right picture is on half densities, this kind of wrong picture is on functions, but then what about this very nice, very important equation? What was it on half densities? This equation?
Oh, but I mean, this equation simply says that the principal symbol of the differential operator is the Poisson structure. And the principal symbol is still, if it acts on sections of some line bundle, the principal symbol is the same thing.
What's the equation? See?
Yeah, okay. Sorry, now I'm not prepared to write it down, but it's I mean, no, of course, like principal symbol is something very easy, right? So
okay.
I don't know how to write it down this way, but
now, what confuses, it uses the product of functions, which was forbidden before.
Yeah, so you can multiply half density with a function.
That's good.
So that's the only, I mean, that's going to enter into the definition. That's not necessary.
Okay. Okay. Yeah, we can take it as homework.
Yeah. Oh, I should have said that. That it will.
See, I'm trying to be helpful.
Yeah.
If you just multiply that equation with alpha 0, will it work?
Yeah, of course it would, but okay. Now I didn't want to. I didn't want to use a particular alpha zeros and use the fact that it's everywhere non-zero. But yes, I guess if you just multiply it and put it there, and then you don't need to suppose that it's actually invertible, then that would be the right equation. Yeah, you're right.
Mm-hmm.
Okay, so there is a almost but still about 15 minutes maybe. So okay, what other kind of fun stuff one can do here? As I told you, maybe I erased it in the meantime, that somehow there was no space for product of differential forms in this picture. So where is, but normally there is product on differential forms. So where does it come from? So I'll just write a kind of a remark and I'll leave everything else as homework. So the product on this guy, which are those half densities on T star of M. So where is it coming from? It really comes from the fact that it's just for those people from Poisson geometry community probably, but there are a few of them here. So it comes from the fact that this guy is really a symplectic groupoid. And basically the story is that this gives a structure of a associative, actually commutative algebra here because it's a commutative symplectic groupoid. But the nice story is that if you start with a non-commutative symplectic groupoid with something more convoluted, something integrated, some structure, then you get a non-commutative algebra. And so all of these things beautifully work here. So there is some kind of very easy quantization of things in some sense.
Oh, what's a nice example where you get some non-commutative product?
Okay, let me put it this way, that if instead, okay, let's start with X, which is an odd Poisson thing. So it is supermanifold now. It has to be a supermanifold. And then we integrate it to a odd simplicity group weight. So this guy. And now, so we take half densities here, and they turn to a non-commutative differential algebra. And what this guy then gives, those half densities, 1/2 of gamma. It's a sort of deformation of differential forms on X. I mean, as a differential algebra, and I of course don't remember.
But then, what X would it work? Say with gamma cotangent bundle of some supergroup? Or
Yes, totally.
So X,
so then you basically get into play the let's say enveloping algebra of the tree algebra, depending on what kind of half densities exactly you're taking, or some kind of convolution algebra of the group. Yeah, I think the thing was somehow, if you well, let me just leave it like that. So there is a natural deformation of differential forms, and actually every filtered differential deformation of differential forms, so this is a graded thing normally, so we can look at filtered deformations, and they are in one-to-one correspondence with odd Poisson structures on X, and it goes through those. So this group weights.
and you have a paper on that, right?
Apparently. Yes. Anyway, so I want to skip something, and so that's the reason why this talk looks like what it looks. So let me talk about another paper of mine. I sort of complained a little bit about the theorem of Diablerets because there were always coordinates in those statements, which is okay. In some sense, it's totally fine. So, but let me now put it in this way. So, invariant. Let's say description. Probably the worst thing about all of this are those Berezinians. So if you know them, then you know that they are horrible, and if you don't know them, then no. Just stay with your life. So there, some of the real construction goes like that. So we have our odd symplectic M. And then we take differential forms on this M. There are two differentials. One of them is the Ram differential, and the other one, as was already mentioned, is this little omega, the symplectic form, because it squares to 0. So like wedging with omega, so this is a bicomplex now. And so what are now those half densities? There's 1/2 M. I said that there is a natural definition, you don't have to fight with square roots. And the thing is that those Berezinians, they are actually naturally defined as the cohomology of some Koszul complex. And let me just put it, what it actually is here. It's the cohomology of omega M with respect to that differential. So if one goes into the definition, it actually becomes clear that this really squares to densities on M. So it's a nice thing. So this is understandable. This is not understandable. And if you have a bicomplex, then we should do now spectral sequence. So the next difference on the spectral sequence would be 0. So D acts by 0 on this guy. But the differential after that is non-zero. So delta is simply D composed with, as it would be in the construction of the spectral sequence. And then we have to invert this differential and then, okay. So it's like the third, or I don't know, or second, not sure which one, differential in the spectral sequence.
Oh, but then what happens then? Or then it stops? Or I mean...
Oh, yeah, then it stops. There are no further differentials anymore.
Mm-hmm. So the cohomology of delta is the cohomology of the total complex?
Yes, indeed. And it's just Durand cohomology.
No, I mean here you don't have a Durand setup. What would I mean Durand?
Oh,
Durand of what? Of the body.
Oh, but okay, you can. It's even like cohomology just of this with respect to D is the same. Somehow it doesn't change anything in the end. Yeah, it's true that it's the total cohomology, but it's also like just cohomology with respect to D. So everything somehow collapses. So the cohomology is non-trivial, but typically finite dimensional. Okay, and let me finish this non-talk by maybe, sorry for moving so much. Again, coming a little bit back to this remark, this would be a little bit old-fashioned way of seeing things, that when we choose some underlying half density and do everything with respect to this. So what's actually happening in algebra to respond to that? I don't have much time, but let me tell you something. Or algebra / topology. How is that? So if you stay just with symplectic, or let's say odd Poisson things, so or there are also what are called Gerstenhaber algebras in the end. So if you have something with an odd Poisson structure, roughly speaking. So what's happening there? So if you have an associative algebra, and we compute the Hochschild cohomology of that guy, then this stuff is a Gerstenhaber algebra. So there's a cup product and it has a bracket, right? And if, let's say, if A is C infinity of M0, and okay, I shouldn't say that we need to take some kind of local Hochschild cohomology, but whatever. So then this HH, those would be exactly polyvector fields. B of M0, and now the would be topological part or counterpart of that is that when we take the little disk operator, little disks. So that's the space for every n. We have the space of all configurations of small disks in the unit disk, and it forms an operator because we just can shrink such a configuration and plug it into any of those windows.
It's all 2D.
Yeah, it's 2D. Yes, I should put, let's say, 2 disks. Then, how is it going? That when you take the homology of this LDO, then we get the Gersten number opera, so the operations which act over there. And then there is this beautiful story about all this, that chains of these guys, chains of LBO that act on axial cochains. So this is what is called the ring conjecture, and was then proven several times by several people and always disproved. But probably it's the theorem of McClure and Smith, I guess now. Finish up all of this story. So the thing is that this operand is formal. Which is a theorem of Tamarkin. So which then that means that those axial chains, they are sort of Gerstenhaber, they form sort of Gerstenhaber, there is Gerstenhaber infinity. So that's what's happening with just associative algebras, and we only see kind of the Poisson bracket here, right? So we only see this. So where is the BD story now? So the thing that I'm right now erasing so it appears if we have a which is a Frobenius algebra, then the axial cohomology of A is now a BD algebra. And the corresponding story for like this topological thing is when we take the framed little this operand, and everything works just as before. So the particular case would be that A is like C infinity of M. But we need a volume form, right? We want to make it to a Frobenius algebra. So with a volume on M0. So it's a story which is just kind of very beautiful, but it requires a particular choice of a trace. But there is a story which works just for algebras again. So the third thing is just an associative algebra. And then one needs to take a pair. Sorry, I should have stopped probably. Oh, no. I'm at the end. We take the cohomology and the homology. And when A is C infinity of M. So we get, M0, we get then polyvector fields on M0 and differential forms on M0. And this pair now is what is called a calculus algebra. A calc algebra. The thing defined by Tamarkin and Cigano, this thing. And I will not write down what it is. It is just all operations that you can imagine here, except for the product of differential forms. So it's precisely what's happening in the BD story. But why don't we have a product here? Because if you write down the non-commutative story, there is just no place for the product there. And yeah, so the corresponding operand here is two-colored, so it's composed of the little this operand. So it's one color, and this will be my final picture. And plus, there is a second color. which corresponds to those half densities would be, or to, in the end, to Hochschild chains, if you wish, where this kind of cylinder. Cylinders can be stuck together. There is a framing on the cylinder, so we somehow remember, say, a point here and another point there, so we have to rotate things before plugging them in. And then there are holes, circular holes in the cylinder, so there we simply plugging in these things inside. So in that way, it forms a two-colored operator, and that's the story. This is what gives us